Hey guys, video 2. What you're going to want to do is going to keep this chart out from video 1 about birthdays. We're going to continue on with some of the questions off that to kind of explain everything. Okay, so the next question that we have for us is, it says to calculate the expected counts for the two age groups, assuming that there's no difference in the distribution of birthdays. And if you remember from previous notes and examples, we said that if the distributions were different, then we couldn't do the chi-square. Same thing happened with our t and our z, not our z, I apologize, our t and our our z. If they weren't normal or if they didn't fail anything like that, one was skewed, one was normal, then we couldn't do our distribution. Okay, so that being the case, is we need to do our expected counts. Okay, so our expected counts is found in a two-way table. So now remember, we're dealing with two-way tables. Okay, so our expected counts is going to be column total times by our row total divided by our table total. All right, so if we come back to here, our column total is 77, our row total is 21, so we multiply those two together, divide by 150, and that's going to be our total for our expected total for this one. Okay, then we do 73 times 21, divide it by 150, and that's going to be our total there. So I'm going to make another chart with Sunday, Monday, Tuesday. I'm going to put the two columns here, and then what I'm going to do is I'm just going to put the expected counts. Okay, if my mouse will work. Okay, so here is my expected counts. I have calculated them all by, again, taking the row total from our table, multiplying it by the column total, and dividing it by 150. So that's what you should have gotten. Okay, now the next part is the part I really hate saying. I don't mind doing it. It's, again, my language barrier, whatever you want to call it. But it's going to sound funny, and it's okay. All right, so we're going to talk about conditions for performing a chi-square test for the word I really hate saying. Homogeneity. There you go. That's why I hate it. Anyway, so we don't have to worry about independence this time, which is kind of weird, because we're actually going to be testing for independence later on with the chi-square that we get to look at. All right. So, but it's the same conditions. We've got random. We've got our 10% condition. And then if it says that it's without replacement, then I think we are even better off without having to do the 10%. We'll get to that here in a second. Our large counts, all of these have to be larger than 5. Okay? Great. All right, so I'm going to pause it real quick, and then we will go and have some fun. Okay, so our problem we're going to continue with is our birthdays. So remember the tables. We've got this guy here that shows our expected, and then this guy way out here shows our observed. Okay, so what we've got is we need to calculate our chi-square statistic. That is our sum of the observed minus the expected. We square that, and then we divided by the expected values. Okay, so what I did is I went ahead and wrote it all out for you. Now, I know the calculator can do this, but remember, we want to show you the difficult and horrible way of having to do it longhand before the calculator would do it for us. It might take you a good 8 minutes to type that all in if you do it right. Okay, so once you get it all done, we get 6.55 as our chi-square statistic. Okay, so the next part, we're going to keep working through this, and we're still going to be using the birthday problem, but we're going to talk about our degrees of freedom. Now, we're dealing with a two-way table. All right, so what we're going to do is we're going to take the number of rows and subtract 1, and then we're going to take the number of columns and subtract 1. And then that's going to give us our degrees of freedom, which then allows us to go to our table and calculate our answer. Okay, so if we were to do this real quick for our degrees of freedom for our birthday question, we have 7 rows because there's 7 days. And then number of columns, we have 2. So then 7 minus 1 is 6. 2 minus 1 is 1. So our degrees of freedom is 6. Probably one of the easiest math questions we'll be doing all day. All right. So I'm going to pause it again so that we can keep writing and not wasting your guys' time. Oh my. Okay, so we're going to continue with the birthday problem. Hopefully we're going to finish it up. We will finish it up. Anyway, we are going to state the hypothesis. B, we're going to verify the conditions for the test are satisfied. We'll use table C to find the p-value. Then we'll use our calculator. We're going to interpret the p-value from the calculator in context. And then what conclusion would you draw? And we're going to justify our answer. All right, so a solution. Let's go to our null hypothesis. Okay, now again, we're doing chi-square, so we're going to be writing something out. Okay, so we're going to say there is no difference, because we're dealing with a two-way table, in the distribution of birthdays for people born before 1980 and people born after 1993. Then our alternative hypothesis, okay, again, I know it's capital A, but just to make it easier for us to read. So then we'd come here and say there is a difference. And just to save ourselves some time, there is a difference in the distribution of birthdays for people born before 1980 and people born after 1993. All right? All right. So there's our hypothesis. Okay. Then we're going to go to B, which was verify the conditions. And the random, way back when, I know it seems forever for us, that was stated. All right. Then we're going to go to, let's just do a 10% condition. 77 is less than 10% of all people born before 1980. And then we're going to have 73 is less than 10% of all people born after 1993. Okay? And then we already did our large counts, and they were all above 5, so we're good there. C, we need to do our table. All right. Let me pause real quick. So going back to what we already calculated, we calculated our degrees of freedom to be 6, and we did our chi-square was 6.55. So I'm going to come to here. Degrees of freedom was 6, and the smallest value is 7.84. All right. So that means for us, our p-value is going to be greater than 0.25. All right. Now, going to our calculator, what I'm going to do is I'm going to go to second distribution, come down here to my chi-square CDF. All right. So chi-squared CDF, that's again a little bit slower. Second distribution, pulls up that. I'm going to choose number 8. So my lower value is 6.55, upper is 1 E99. Degrees of freedom was 6. And we get p-value of 0.3645. Okay, so then we're going to come into here. In part D, the question was interpret the p-value from the calculator in context. All right, so we're going to start with assuming that the true distribution is the same. So basically what we're saying is the null hypothesis is true. There is a 0.3645 probability of observing a difference in the distribution of birthdays among the two age groups as large or larger than the one in this study. Okay, so we're just going to say that the difference between the two of them just by chance alone is going to be about 0.36. Kind of high. All right, so E, wrap it up. Well, if we go back to here, our significance level, because it wasn't stated, it's going to be 0.05. We are going to reject, or sorry, we're going to fail to reject H naught, and then we'd write out our conclusion sentence. Okay, we failed to reject the null hypothesis. We do not have convincing evidence that there's a difference in the distributions of birthdays for people born before 1980 and people born after 1993. Okay? Alrighty. We'll get started on the next stuff.